Hello, for today's video lecture, we're going to be talking about mass moments of inertia via the method of composite parts. So as an alternative to the use of integration for finding area or mass moments of inertia, we can use lookup tables along with the parallel axis theorem to find the combined moment of inertia for a composite body. In this way, we kind of skip the integration and instead use the work of others as a shortcut. All those tables were generated via the integration method. So this is similar to what we did for the centroid or center of mass for a composite body, and also what we just did with the method of composite parts for areas that we discussed in the last section. So overall process is going to be as follows. So first we're going to break the composite body down into simpler shapes that are all available in our lookup tables. We're going to look up the moments of inertia for each individual shape using the moment of inertia tables. We're going to use the parallel axis theorem to adjust the moments of inertia to a common origin point, whatever we're rotating the body about in this case. And then we're going to add the adjusted moments of inertia together to find the overall moment of inertia for our combined composite body. So stepping back to the first step, we've got the first step in finding this is to break the shape into simple shapes that are in our moment of inertia tables. So our mass moments of inertia are all going to be 3D shapes. If it has mass, it's going to have some volume in there as well. So example shape I've got over here is our hammer. So this hammer we would need to break into 3 separate pieces. So part 1, we've got a rectangular prism. That's kind of the head of the hammer. Part 2 is actually, it's pointing to the cylindrical cutout that we had in that. So that's going to end up being kind of a negative area. We're going to remove that mass. And then shape 3 is going to be the cylindrical handle that kind of goes up the middle. So it's also, at this point, it's going to be useful to identify some axes and an origin point. We're going to need to be consistent with that through the problem. So make sure that you've got that X, Y, and Z axes labeled in your diagram, and we know where we're measuring all our distances from. All right, so now we've got our shape. Next, we're going to kind of create a table to keep track of various values. So down here, this is a table that's going to work for our piece. So each row is going to be used for a single part. So we've got 3 pieces to this: shape 1, shape 2, shape 3. We're often going to have a total row at the bottom there. And then the columns are going to vary from problem to problem. Sometimes we need to find all 3 mass moments of inertia, so about the X, Y, and Z axes. For this one here, we're just looking at the I-Z values. So there's the rotation about the Z axis in this case, kind of how you would swing a hammer. So mass, what's going to be important with this is the height of the center of mass of the various pieces, IZZC. This is going to be the numbers that I'm looking up directly from my table. I'll need to plug in things like mass, height, width from that. I'll need to know how far I'm adjusting it with the parallel axis theorem, and then finally the adjusted moments of inertia is the last column that I'm going to have. So after determining the mass of each piece, this can be either given or we can do volume times density if it comes to that. The next step is to determine the center of mass of each piece as well as the overall center of mass location for the composite body. So we'll often be taking the moment of inertia about the overall center of mass. So if a object is just kind of like moving through space, it will tend to rotate about its center of mass. Not always though. So sometimes we are going to be taking the moment of inertia about a different location. So our hammer example, I am going to swing the hammer about the base. I'm not going to swing it about the center when I'm using it. So either way though, we are going to need to know the location of the center of the mass of the individual pieces. We're going to use that for the R values, the adjustment values that I have in the parallel axis theorem. So next we're going to look up and calculate moments of inertia about individual centers. So for my hammer piece, an example for the handle, that cylinder piece 3, honestly for the cutout at 2 as well, I'm going to have the following equation that I would use. So orientation wise, this does already line up. So the Z-axis here is the same as the Z-axis over here. So I can use IZZ. I might need to rotate that so that it matches. Try to kind of figure out what axis you're actually using in the problem. But in this case, IZZ is going to be 1/12 times the mass. It's going to be mass of the handle times 3r squared. R is going to be the radius of the cylinder plus h squared. So with all of this, you'll just need to kind of gather numbers that you have from the diagram itself. I don't have any measurements in here, but generalized, that's what you're going to do for that. Next, we need to adjust with the parallel axis theorem. Again, remembering our piece, so parallel axis theorem that we would use in this case is IZZP, which is the mass moment of inertia about any point P. It's going to be the point we're adjusting to is going to be IZZC, which is the mass moment of inertia about the centroid of that shape. These are the numbers that we just got from the previous step, plus mr squared. So m is the mass of the part, and then r is how far we're adjusting this. So it's the distance between the z-axes, going through C and the z-axis going through point P that I'm adjusting to. So the r value represents the distance, and this is the adjustment piece of this. So we're going to use the center of mass values in our table to find the adjustment distance r. That's why we found those distances or those locations earlier. So in some cases, we're going to adjust to the center of mass. So if I'm finding the moment of inertia about the center of mass, I would have something like this. So the center of the cylinder is going to be somewhere around here. Center of mass of the whole thing, of the whole hammer, is going to be somewhere closer to the head because most of the weight is up at the top here. So this might be my RZ value. I might also be looking at something like this. So rather than the center of mass, which would be the kind of hammer just rotating through space, I might also look at the moment of inertia about the base. And if I am adjusting everything to the base, RZ is going to be going from the center of the cylinder down to the base of the cylinder. So RZ might be that. So it depends on your problem. You'll need to figure out where you're adjusting to earlier on, and kind of use those R values as necessary. And there is going to be an R for each of the pieces. So there'll be an R for the head of the hammer, R for the cutout, and R for the cylinder that we have there. So once you've figured out your R values, you're going to use those to find the adjusted moments of inertia for each piece. So again, parallel axis theorem, we're going to take the IZZC values, which are in our table. It's what we had from our kind of moment of inertia tables, plus mr squared, so m and then r there, and get IZZ adjusted. So all of it, fill out the IZZ adjusted values in your table, and then once they're all adjusted so that they are all taken about the same point, we can simply add those values together. So the overall moment of inertia I'm looking for is this value down in the bottom right corner, which is the sum of everything that we have above it. All right, so that's all I have for today's video lecture. Thank you for watching, and I hope to see you again.